The grade book is going to be in flux in Canvas for a few days. I don't know if you remember, I had first assigned way too many problems in the sections, and it won't let me edit the number of problems, so I have to remake all of the assignments. But Canvas had already connected to all of the old too many homework assignments, so I'm gonna have to delete a bunch of stuff out of Canvas and re-import it from my OpenMath. For the next couple of days, things are gonna get weird, perhaps. I'm not sure how it's gonna work, but I think I've straightened out most of chapter 6 except for section 6.6. So the homework and grades might get a little funky over the next few days. Let's see, what else do we have here? Modules. Yeah, so for example, like the 6.1 and 6.2 that was in week 4 disappeared because of the weird settings. So hopefully everybody turned in quiz 1. I graded a bunch of them over the weekend. Anything that came in late, I haven't graded yet. And then there's going to be a quiz 2. I see some people already did that. If you haven't done your quiz 2, please do it. And again, a reminder about the quizzes for the rest of the quarter. Every section, I am going to pick 2 problems like the ones in your homework, and you need to show me your work on paper and then scan it, take a picture, give it to me in class, whatever. Somehow get it to me. Because I need to see your written work just to make sure your technique is good. Because I think that'll help with the test more. Because a lot of people had right ideas on the test, but their technique was a problem, and then things went to hell. So I think that's going to improve test scores. So let's see, I started putting together a week 5 down here. Let's drag that up. Come on. I can't believe it's already week 5. I think it's, that crazy first couple of weeks. So we're tying up section 2 today. We're going to start section 3 probably. That's about arc length. Section 4 is we've got all these crazy things we've revolved around the axis, right? And we've looked at how much they can contain. Well, how much paint would it take to cover them, right? What's their surface area? So that's what we're going to take a look at after arc length. But first we have to do arc length. And then in section 5 and 6, we start doing some physics. And I'm going to send out a little physics, not really a quiz, it's a survey, because I want to know what you know about physics, because I want to make sure everyone's on relatively equal footing when we start doing that stuff. So how much physics I need to cover versus how much I need to focus on the math, right? I don't know. So I'm gonna send out a survey probably tomorrow or the next day, and later today or tomorrow a quiz 3 will appear that you will be able to see that it has 2 questions like the homework ones. How many of you actually read the book? We got a couple. Okay. Has anybody noticed any similarities between the quiz and the examples in the book? You have noticed? Oh, good. Okay. So I was hoping somebody would notice and bring it up, but no one brought it up. What's that? One of the examples in the book is exactly the same as the quiz question. And I'm going to do that all the time now. I'm going to pick one of the examples out of the book, which there's usually a homework problem just like it too. I'm also going to put that question on the quiz. So one question you should not miss. You just need to scan the book and figure out which one I put in there. Okay, so I'm trying to force you to read the book. You could just, but in a class like this, it's really beneficial if you want to do well to read the book, attend class, and do the homework. It's like a 3-prong approach to it. And if you've survived in math this far, not reading the book, you're not going to make it much farther unless you're a super genius. And I know very few super geniuses. There's not many out there in the world. There's a lot of really smart people. Most of you are probably smarter than me. Like I said before, I just happen to know math at this point in time. All right, let's do some math. So we are going to take a look at that related rates problem. So let me bring it up from the homework. So read the book. You'll get a surprise on that quiz each week, each day, each section. There we go. Oh, here's the other thing that's super important. With online homework, I've noticed that some people have a bad habit of, if they don't know how to do it at first glance, they hit the show me how or help me solve this or give me an example, and they get the answer and then they move on, they're done. What that means is you were doing the problem with a tutor looking over your shoulder. Is there a tutor looking over your shoulder nodding yes and no as you take the test? The answer is no. So every time you use the show me an example or help me solve this, then you also want to do a similar example after that without any tips. Otherwise, that you don't have the skills it's going to take to do it on your own on the test. So super important. Please, please, please. Password, what is it? Please get it done. Is that right? Please get it done. All right, and I think it was problem 17. Let's see if I'm right. Come on. No, we're going to do that one too. That is the torus problem. Is before that one? Nope, maybe it's after that. Ah, there we go. Hemispherical bowl. Okay, so 2 parts to this. First, we will calculate the volume of a hemispherical bowl up to a depth h, and then once we have that, we can use that to then look what happens as water flows into that bowl at a constant rate and see how fast the height changes. Okay, since the width changes, right, as you go up, the height's going to change different than the volume, right? Okay, so it's gonna rise fast at first and slow later because it's opening wider. So let's see if we can sketch that. So let's see, we have a radius A and a height h of a hemispherical bowl. And there's lots of ways to set this up. Let's see, I gotta sit here and do this. My pens are gone as usual. Apologies in the recording, I have a cough drop in my mouth, so I have a sore throat. So, don't breathe too deeply in this room. Just kidding. I'm pretty sure I'm not contagious. Pretty sure. All right, so if it's a hemispherical bowl, that means we're gonna have to deal with a circle. Most basic circle we usually deal with is something like x squared plus y squared equals a squared, okay? If I want it to hold water, then that means I really need to look at the lower part of the bowl. So from A over here to negative A over there, we have A down here, or negative A, excuse me. And solving this for y would equal plus or minus the square root of a squared minus x squared. And if I want my bowl to hold water, I want this version of it. And so I'm going to choose the negative one. So I want y equals the opposite of the square root of a squared minus x squared. And then we're going to choose some value here. I'm going to call that h. H is some y value. It's a negative number in this case. And if we revolve this thing, let's take this chunk right here to revolve. That's at some height y. I'm going to spin it around and I'm going to generate this disk. This is still the disk section. Okay. Let's see, other things to note. Oh, I keep violating my first rule of these pictures. Write down whether that's a dy or dx right away. Once I note that, I realized I solved for the wrong variable up there. But this is a symmetric equation, isn't it? With x and y. So reversing that, I'm going to get x equals let's see, plus or minus square root of a squared minus y squared. All right, so now I got to rethink my picture for a second. Notice this is x equals. X is a horizontal variable, so that means the positive is the right side and the negative is the left side. So for example, this dotted line right there is x equals the positive square root, that's an x, of a squared minus y squared. So really here, I'm just revolving that quarter circle around when I generate my bowl. Okay, so now I have that rewritten. So some things to consider here. The radius is that x length right here of my cylinder, which is this guy right there. So r is equal to the square root of a squared minus y squared. The thickness of each disk, again, is dy. The area of the top, that would just be pi r squared, right? Let me switch colors. Pi, my radius, is the square root of a squared minus y squared squared dy. So that right there, given some thickness dy, represents the volume of this disk. And we want to integrate that with respect to what variable here? Y, okay. And keep in mind y moving like time goes from bottom to top. So what would be my starting y value here? What's the lowest y value? Negative a is the lowest y value. So I'd be integrating from negative a up to, not 0. Well, if I wanted the whole hemispherical bowl, I would go up to 0, correct. However, the problem asked me something a little different. It said find, for a hemispherical bowl of radius a contains water up to a depth h. Yeah, so that's why I drew the h in there. It's some height inside that hemisphere, somewhere between negative a and 0. And so that's why I threw that in there. So we just want to go up to h. So what this will give us when we're done is this will be a function of h, because h is some height, right? So we'll come up with a function that talks about how much water is in a hemispherical bowl, somewhere between the bottom here and the top is what we're generating, okay? All right, so we did the hard part, the setup of the integral. So again, what we've calculated here is a volume that's going to depend on the height, right? That height right there. Fortunately, we get to square the square root, right? So let's clean this up a little bit. So I'm going to pull the pi out. I'm integrating from negative a to h, and I have left inside an a squared minus y squared. And it's always a good idea if your integrand has pluses and minuses to put it in parentheses to be safe. Remember, a is just some constant. It's the radius of the thing we revolved, our little quarter circle there. And so when I integrate through this, the antiderivative of a constant here is the constant times the variable. So I'm going to get an a squared y. Antiderivative of y squared with respect to y, that's going to be y cubed over 3. And that's all happening as y goes from negative a to h. Keep in mind here, we have two non-zero boundaries, which means we have to do a subtraction and be careful with our signs. Okay. So let's see if I can steal that to a new page. So now we need to evaluate that. So my volume again is equal to pi times a squared y minus y cubed over 3 from negative a to h. Plugging in the h first, I'm going to do that underneath here. I'm going to get a squared h minus h cubed over 3. I should probably put curly brackets around that and put my pi in front before I forget it. Anytime I have something complicated and two boundaries to plug in, always a good idea to go minus parentheses. Otherwise, signs could be a problem. SIGN, sign, positive, negative. All right, what do we get here? I'm going to get an a squared times a negative a. Just going to be careful here. And I'm going to get minus parentheses negative a cubed. Always a good idea with substitutions to put your substitution thing in parentheses if it's not trivial. All right. Cleaning this up, what do we get? Not much I can do here. So I'm going to get pi times a squared h minus h cubed over 3 All right, so let's see. Here we're going to have, let's switch colors. Positive times a negative is a negative, but I also have to distribute this negative through. So I believe that's going to give me a plus a cubed. And then here I have a cube that's negative times this negative here. So those guys should cancel out, but I'm distributing a negative through. So it looks like that's going to be a minus a cubed over 3. And I don't know if it's worth cleaning that up right there. We could factor an h out of it. I don't think I want to do that. But this cleans up right here, right? 1 a cubed minus a third of an a cubed is going to leave us with 2/3 of an a cubed. So it looks like I get pi times a squared h minus h cubed over 3 plus 2/3 a cubed. And this is our volume function, and notice it's in terms of a and h. Now in this situation, we're thinking a is a fixed number like 3 or 5 or 1. H is the thing that can vary. So I'm viewing this as a function of h, function of the height. Okay, so we have our volume function. Now we're ready for part 2 of the problem. It says, all right, let's let water run into the hemispherical bowl and let's let the radius be 5. Okay, that's good. We let have a be a number. So that takes one variable out, which is nice. And then the water's flowing in at 0.2 meters cubed per second. Okay, so that's volume over time. How fast is the water level in the bowl rising? So now we have to try and do that. So what's that? Oh, and then when the water's, yeah, when it's 4 meters high, yeah, because it's going to vary. It's going to be different at each point. So a couple things to consider here. So we have our function here for volume. And let's go new page. They give us the rate at which the volume is running in. That's dV dt. And they're saying dV dt is 0.2 meters cubed per second. Other information we're given is that the radius A is 5 meters, and we want to look at the instant in time when the height is 4 meters. Okay. Other things, thinking back to calculus 1 when you did related rates, the height changes, right, as the water comes in. So the volume is a function of the height. Okay. So technically, if you integrate with respect to t, a function of another variable, chain rule says that's dv dt times, let's see now, dv dh, excuse me. Where's my eraser? Oops, oh gosh, what did I do? Wrong button. dv dh times dh dt is what we get from the chain rule there. All right, so let's see. What's going on here? Well, this thing right here, again, that's my dv dt. We're given that. We want to figure out what is that guy right there. So that leaves it up to us to find this missing piece right there, dv dh. Well, we just calculated v as a function of h, so we just need the derivative of that guy right there. Now, before I do that, I just want to make a note on the previous page. On the previous page, let's see, switch colors, highlighter. We found that the volume was equal to that integral, right? What happens when you take the derivative of an integral? They cancel. Yeah, so we can apply the fundamental theorem of calculus to this guy right here. Meaning if I only cared about how fast the height was rising, I didn't actually need to do any of that right there. Or on the next page, any of that. So why did we do it? Well, it was fun, kind of, right? So I'm just going to take a note. We have this right here, right? So that was pi times our radius squared. So back here, I can find dv dh by just taking the derivative with respect to h of my integral. My integral was pi as y went from, what was it, negative a to h of the square root of a squared minus y squared squared dy. And the fundamental theorem says that if you are taking a derivative with respect to an integral with the same variable as an endpoint, they just cancel out. So this must be equal to, according to the fundamental theorem of calculus, this integrand right there. Squaring that square root, that's got to be just a squared, sorry, pi, don't forget the pi, that's still hanging out, times a squared minus y squared. Oops. What's our upper bound here? H. That's what we're taking the derivative with respect to. If you're unsure of that, if the fundamental theorem of calculus still makes you nervous, then just take the derivative of this with respect to h. And I think you'll find out we'll be all right. Shall we do that just to double check? Excellent idea. Good choice. So if we take the derivative with respect to h of this stuff up there, okay, let's see. A is just a constant, right? So h is our variable. What's the derivative of a constant times a variable? It's just a constant, right? So the pi is still chilling out front. Parentheses, derivative of a squared h with respect to h is just a squared. Derivative of h cubed over 3 is what? 3h squared over 3, which is just h squared. So we're going to get minus h squared. And what's the derivative? Let's see, is a constant or a variable here? It's a constant. What's the derivative of a constant? 0, so I'm done. Okay, so yeah, it checks out. Although we do have a volume function, we didn't really need it here for the related rate part. If somebody said, oh, but what's the volume when the height is equal to h? Well, then I need this. Then I need that. Okay, but we're all right. Okay, so now we just plug in what we know. So in this case, we want to plug in a equals 5 and h equals 4. So we're just going to evaluate dv dh when a is 5, that's a 5, and h is 4. And so that's just going to be pi, parentheses, 5 squared minus 4 squared, 25 minus 16. On a good day, that's 9, isn't it? So that's 9 pi. Am I doing all right? Back to what the chain rule tells us here, new page. Chain rule again says dv dt is equal to dv dh times dh dt. We were given dv dt is 0.2. We just calculate when a is 5 and h is 4 that dv dh is 9 pi. And so now we can find dh dt by solving. So if I just divide by that 9 pi, dh dt has to be 0.2 over 9 pi. I just want to do a quick check of the units. I know you guys that have taken physics do a lot of unit checks in physics. So a reminder, the 0.2 here was meters cubed per second, right? The dVdh, what's that going to be, that 9 pi? Well, V is measured in meters cubed, and h is measured in meters. So that means what? dH/dt is essentially meters squared, right? So I have meters cubed over s times the reciprocal of meters squared, which is 1 over meters squared, which equals what? Meters per second for the units. So I'm just analyzing the units there. Is that an appropriate unit for dH/dt? Yeah, that looks good. So it looks like we got the units right, and we have a numerical part. This is the exact value. It'd be nice to get an approximation. So let's take a quick look at the approximation on that. Calculator. What is 0.2 over 9 over pi? I get 0.007 when I calculate that. So that's about, oh, my pen is freaking out. Come on, there you go. So it's about 0.007 meters per second is how quickly it's rising. It's not rising very fast at that point. What do you think would happen if we measured the rate of height increase if we did it down here instead of way up there? It'll be faster, yeah, because it's not as wide down there. It's narrower, yeah. So it'll be faster down there, yeah. So the height will increase quicker down here and slower up there. Okay, boom, we did that. Let's take a look at that torus problem again. Unless somebody has a homework problem they're dying to do. No homework problems anyone's dying to do? Okay, torus. All right, so the torus problem, I had started doing it in class with disks, and we can reevaluate that idea. But the idea was to take a circle of radius A, and then take a number B that's greater than A, and make a vertical line there. And then revolve around that vertical line. And when we do that, we're going to make a donut or a torus. Okay. And I am not good at drawing a torus with this pen, so I'm just going to ask Google to show me a torus. Oop, 1R, sorry about that. Okay, oh, there's a lovely torus from Wolfram Alpha. Look at those. Let's click here. It's going to show me the full picture. I think I clicked the wrong button there. How about that one? Come on. A few of my favorite spaces. The torus. Oh, look at that, a glazed torus. Oh, the images aren't loading here. Oh, Scientific American. Oh, I'll have to check that out later. Come on. All right, Scientific American is not loading very quickly, but you get the idea here. So here's like a torus made out of plates. Okay, so we're revolving our circle around a line, we get a torus. So we're going to calculate the volume. When we did it in class the other day with disks, we kind of rushed at the end of class, so I just want to slow down and do it again. There's only 1R. All right, so a couple things to consider. If we're going to do this with disks, the disk has to be perpendicular to the axis. I also did it with shells when I was playing around the other day. It's not much easier doing it with shells. I think it's just as hard. So that means I have dy's here. So considering that the equation of a circle centered at the origin is x squared plus y squared equals the radius squared a, we want to solve for x to get a function of y here. So for us, we get x equals plus or minus the square root of a squared minus y squared when we solve this for x. So now I have a function in terms of y. Now keep in mind, x is a horizontal variable, so the plus is the right side, the minus is the left side. So maybe I'll color code this. The minus would be this side over here. okay? The plus would be that black side over there. So let's see. When I look at, how about, let's say we're doing discs, straight discs, or is this going to involve a shell? Washers, that's what I meant. Sorry, washers. Thank you, Darren. Washers, yeah. So with washers, I'm going to have an outer radius, which is going to be the distance out here, capital R, and I'm going to have an inner radius, which is right there. The outer radius is related to the opposite of the square root, right? Now, if, again, we're looking at x as a horizontal variable here, right, to get the length there of our rectangle, that means we want to take the greater number and subtract the lesser number. So for big R, I'm going to have b minus negative square root of a squared minus y squared. That cleans up nice to be b plus the square root of a squared minus y squared. Switch color. For little r, the greater number minus the lesser number, that's going to be b minus the positive square root of a squared minus y squared. And our formula for washers is the integral, in this case y, pi times r squared minus little r squared. In this case, it'll be a dy. And let's see, where is y ranging from in this situation to get a full donut? From negative a to a, right? So given the symmetry here, we have a semicircle on top and a semicircle on the bottom. We could make our life easier by doubling the integral from 0 up to a. So I could put a 2 out front and go from 0 to a. Now, what that means, however, is I have to square each of these guys. Okay. So that rather than carrying around all of this notation while I square it, I'm just going to clean up big R squared minus little r squared on the side, and then we'll come back here. So new page. What's going to happen when I take b plus the square root and square it, and then I'm going to have to subtract b minus the square root squared. The b's will eventually cancel, but we just want to be careful with this. So again, to square something means to multiply it by itself. You can't just distribute a square through a sum. So this is b plus the square root times b plus the square root. Oops, I should have done that in blue. Blue. It's better. And here we have our a squared minus y squared, a squared minus y squared. So I'll have a b squared, right? I'll have a b times the square root and the square root times b, so I'll get 2 of those b square roots. And then we'll have the square root times itself, which is just going to be a squared minus y squared. Similarly, I got to do the black one over there. So I have to subtract b minus the square root times b minus the square root. And so I'm going to put an extra set of parentheses in here. I think I'll draw them in as curly brackets. That's going to give me, similar to this, I'll get a b squared out front. Then I'll have b times the negative square root and the negative square root times b. So in the middle, minus 2b square root. And then here I have a negative times a negative, which is a positive. Square root times itself cancels, leaving just the inside. So what's going to happen here? We have to distribute our negative to the 3 terms we generated. So that's going to give me a b squared minus a b squared. So like Darren said, those are gone. But here, that's going to give me a positive 2b, which is like that one right there. So I'm going to get 4b square root. And then here I have plus the difference of the squares, and over here I will have minus because I'm distributing the difference of those squares. So those guys go away too. Whew. That's nice. It cleaned up quite a bit. So now we need to take this back to our integrand that we started earlier. Oops, wrong button. There we go. So we just calculated. Now notice we left the pi off, we left the 2 off. We still have those. So I'm going to pull right the 2 pi out front. We have not integrated yet. All we did is clean up that right there. So we still have y equals 0 in the integral up to a. And now we have a 4b square root of a squared minus y squared dy. We're integrating with respect to y, so 4 and b are just constants. So let's pull out our constants. So let's see, we already have a 2 pi outside. Now we have a 4b outside. And then I have to consider what is the integral from y equals 0 to a of that square root. And the book gave a hint on that right there. What is this the graph of right there? A squared minus y squared. That's that semicircle up above, the right side of it. Now keep in mind, here, we're only going from 0 to a. So if I integrate from 0 to a, that part of the hemisphere, I've calculated what kind of area here? A quarter of a circle. Yeah, it's a quarter of the circle because we changed the boundaries. The book's hint was that it was half a circle. And I went with that in that Wednesday class, and so I was off a little bit. So what that means is this highlighted region right there is a quarter circle. So we still have our 2, we still have our pi, we have our 4, we have our b, and then that integral right there is going to be a quarter of a circle, which is pi times the radius squared over 4. Cleans up just a little, the 4 divides out, and that's about it. So what do we have? We've got a constant of a 2. We have a pi times a pi, so we have a pi squared. I think I'll write it alphabetically, a squared first, and then b second. So we just calculated the volume of a torus. So on a test, I wouldn't expect you to do this with the a's and the b's necessarily, but if I gave you a radius a and a line b, I would expect you to be able to do that. The one catch is, did we come up with an antiderivative here? We did not. We just made an observation that it happened to be a quarter of a circle. Right? In chapter 7, we'll learn a trick for coming up with an antiderivative there. But it's we don't have any tricks for it right now. So the only way to come up with the answer here is to recognize this as a quarter circle. Okay, so we are running near the end of time here. So a couple of notes before we break. Let's get rid of the torus for a minute. and the donuts and go back to our class page. So we are a full day behind the schedule. I'll probably post a new schedule soon. Let's see, calendar. So I had anticipated we would finish 6-2 last week. We're tying it up today. So finish your homework if you haven't. We'll start 6-3 tomorrow. So everything's going to get pushed a day out. So the exam will most possibly be on the 15th of next week. Okay, and that's just going to cover chapter 6. What's that? Not a Thursday. Yeah, it's probably going to be on Wednesday. There's a slim chance we might shift it again, but we'll see. But it's not going to be any sooner than Wednesday, that's for sure. Other things, if you haven't already turned something in for quiz 2, please do so. And I made a note in quiz 2 that the first problem is like your homework number 8, and the second one is like your homework number 10. One of these is actually an example in the book. Highly recommend you look it up. You don't have to. Feel free to do it without looking it up. It's probably faster to just do it than read the example, yeah. But if you get stuck, if you're not sure of your answer, look in the book. You'll find something that looks exactly like it. All right, so that's it for today. Get your homework.